Okay, I see more and more people are joining us online. So welcome to this seminar from the UK Acoustics Network, UKAN Plus. Thanks a lot to UKAN Plus for inviting me to talk. And right now, I'm going to talk about surround sound and marine habitats. My name is Philippe Blondel from the University of Bath in the UK. I am French, as you can guess from the accent. In case this becomes hard to understand, or in case internet is not up to speed, feel free to tell us in the chat. Otherwise, please ask your questions in the Q&A panel, and we will go through them at the end of the talk. So the talk is about surround sound and marine habitats. Marine habitats, well, for a long time, we didn't know exactly what it was. If we look at old charts, for example, this one from the 1500s, there be dragons. There were all sorts of weird monsters out in the sea. Victor Hugo, one of the famous French poets from the 19th century, said, "Free man, you will always cherish the sea." It was a very romantic view, but it was not always borne out by the facts. At the same time, or a few decades later, Jules Verne, the French science fiction writer, had all sorts of things about krakens attacking the crew of Captain Nemo, and the oceans were still very mysterious. The first views that we had about the planet Earth, about all the oceans, were actually accessible from satellites, for example, the images from NASA in the 1960s. But what is really in the sea? What happens below the waves? Only acoustics can bring us the answers. And the answer is we live on a blue planet. We know that since the documentaries by David Attenborough and his crew, The Blue Planet 2, the first ocean maps of the 1950s covered the mid-ocean ridges. They revealed how varied the seabed was. We had subduction zones. We had all sorts of features, large abyssal plains. But these maps are not all with the same resolution, even now, and we still know more about Venus than about our own planet. I know that because I did my PhD working with radar images of Venus. We know everything about the planet, and there are still big gaps in our knowledge of the seabed. But we have the tools to do that. And these tools have evolved a lot. In the 1980s, for example, Gloria, the British side-scan sonar, was the top of the range. It was working at a resolution of 6.5 kilohertz and giving images the size of a football field. So, sorry, the pixels were the size of a football field, 60 meters. And you could get images from complete continental zones and mapping around different countries. In the early 90s, Toby, another British side-scan sonar with 30 kilohertz resolution, had a resolution of 6 meters. So in that case, we could see the goalposts. A few years later, higher resolutions, for example, from Woodsole and commercial sonars, was giving us 60 centimeter resolution. So we could see the goalkeeper. And now we have resolutions of less than a few centimeters or even millimeters. So we can actually see the ball. We could even see the stitches on the ball. So in just a few decades, we moved from having one pixel as being the complete football field to seeing the goal, the goalkeeper, the ball, and now we can actually follow the game all over the oceans. These high frequencies are better because they give better resolutions, but they're associated with higher transmission losses. And very often, the transmission is going to be affected by the properties of the ocean. For example, with sound speeds, the seabeds, whether we're imaging at the surface of the sea, of the seabed, or at the bottom, and then we have volume scattering. If you're interested, there is a very good book, which I'm advertising now, available on Springer, and systematizing everything about interpreting sonar images. I was very lucky to sail in all oceans except the Antarctic. I'm not losing hope for that one yet. And what we have is, for example, hydrothermal vents at mid-ocean ridges. I think one of our listeners has been diving a lot in hydrothermal vents, like the Lost City in her time. This is from further south in Lucky Strike, and we can get resolutions of 1 meter or 60 centimeters, map out lava lakes, volcanic cones, different types of hydrothermal vents, and prepare the dives by humans or robots to discover, for example, new forms of life and extremophile life around these vents. What we have done as well is use that to map geohazards. This is a map from the tsunami that destroyed parts of Lisbon in 1755. For a long time, tsunamis were an act of God. It meant people had to pray harder, and it was just happening. 1755, it was a time in Europe where there were much more enlightened approaches to science, and people actually mapped out the height of the waves as they arrived on the shores of Portugal. They had engravings to tell us how high the waves were. We know that the waves were still 2 meters high when they reached the sea isles there. And if you go walking there, you can see some dark sand deposits on some of the dunes, which are coming from this tsunami. So we're able to map where the likely source of the tsunami was. We could actually map out the heights, the profiles, the topography of these, find out we had unconsolidated sediments. This image over a scale of 40 kilometers is actually giving us a view of the source of the Lisbon tsunami, very big landslides there. And we can actually find out how much volume was moved, when it's likely to reoccur again, and how often it has occurred in the past. So that's very useful to map the risks of tsunamis around Europe. That was a European project, but anywhere around the world, and more people are doing that now. We can also map other types of geohazards. I have worked with colleagues in Malta, Italy, to look, for example, at multi-beam sonar images of Malta, looking at different types of habitats, comparing the textures of the sonar imagery and the bathymetry, and finding out all the different types of habitats, what they are. Mapping large-scale terrains, for example, there, we can find out how they're going to be affected by sea level rise, but also map old terrains and how they were affected by sea level rise in the past 10,000 to 20,000 years. So this is very useful to have an idea of the geohazards around Malta. Marine renewable energies are another topic where it's very useful to know more about the environments. If we look at the potential from waves or from tides, we're very fortunate in the UK to have access to a lot of energy. We can do that with wave energy converters. There are different types. They use the movements of the waves to generate electricity. We have tidal turbines, sometimes in arrays. These tidal turbines would extract the energy from the tides, from the currents. But the big question was, how green is green energy from the sea? How clean is it? That was a dossier in New Scientist several years ago. What are the impacts of all these schemes? For example, if we have these big tidal turbines, can animals be sucked into the turbines? We have seal on one end, seal sushi on the other side. Some environmental groups were saying, well, we have to forget about renewable energies at sea. It's not going to work, it's too dangerous. Marine biologists were a bit more gung-ho, saying, well, if a seal is stupid enough to put its head in the blades of a turbine, it's going to die soon anyway, so who cares? So we're commissioned by the British government to look at the actual risks, what happened around these environments. And in that case, what we did was use multi-beam sonar, like this image there, where we can image a large area around the turbines. The turbine would be there, and we can stack images 8 times per second for many seconds, many minutes if we want. We can see the sea surface there, and we can see things moving there. What these things are, well, we can identify some of them because we had, in that case, fishery sonars looking up, so from the seabed looking up there, and identifying at different frequencies and telling us, for example, this is a herring, this is a cod, this is juvenile cod, or this is something which is not a fish. In that case, this particular target is moving as fast as a seal. It is as big as a seal, and it has the behavior of a seal. We don't have visual identification, so we just call it a target there. But we can see how the animals are actually moving around the turbines using the ecosystem, using the environment. This platform, we deployed it around Orkney at different sites with tidal energies, wave energy converters, at control sites with nothing, so to compare the different types of environments. We used radar to image the sea surface. We had professional bird watchers checking the marine birds. Sometimes we can see them diving and coming back with fish. And these places are actually great for ecosystems because they have exclusion zones around them. So no one is allowed to fish there. Very quickly, the fish realize they're safe. But the marine birds realize there are lots of fish around, no competition from fishermen, and the seals realize the same thing as well. So these places are very good for biodiversity. We have published a lot of articles on the concept and first results and the techniques. They're available as open access articles if you're interested. And to cut a long story short, what we can do by deploying for several weeks at a time is check that no animals are harmed. For example, we don't have any seal coming in and seal sushi coming out. The seals actually use the currents to hunt better and hunt more. And the fish ecosystems are thriving around these different devices. So with acoustics, we can actually resolve this debate and provide data, facts to the different fields. These marine habitats can be affected in different ways by climate change, pollution, or all sorts of other changes, for example, human activities. And that's the case for marine vegetation. In that case, I worked with different types of saccharina and laminaria plates. They're acoustically difficult because they are very thin. The thickness of a piece of paper, or the blades themselves can be very thin, millimeters or less, and they have little to no gas content. So it makes them very difficult to detect with acoustics. But they are very important. Seagrass habitats, kelp habitats are the most vulnerable to climate change, but also to other effects like nutrients, chemical pollution, destruction, and over-harvesting. So what we did was look at different types of sonars. The traditional way is to look at single beam echo sounders, looking down toward the seabed and getting images of the algae there. We can see the height of the vegetation. In that case there, we can see a shoal of fish. But the downside is it only sees below the boat that does a survey. With a multibeam, we can actually look sideways. This is an image of the same place. We see a shoal of fish there. We can see with much better resolution. And we have 120 beams covering an increasingly larger swathe of seabed as we go into deeper water. This study that we did was in Kongsfjord in Svalbard, looking at these macrophytes. And it was very useful to compare what they looked like with different types of sonar. So our goal with another European project was to make it more systematic and understand what was going on at different angles. For example, if we look at multi-beam images at different places, if we look at the comparison with single beam sounders going back to these places but imaging from a different angle, what we find out was that the multi-beams worked well for angles less than 15 degrees, so very close to the vertical. Angles 30 degrees to 50 degrees from the vertical, so quite large. And the comparison with single beam sounders was very good. But we had blind zones in which either we couldn't detect the kelp or the algae, or we couldn't detect them well enough to compare with single beam data. And this, we could explain it by the physical characteristics of the algae, running acoustic simulations of what they could be like, and by testing systematically all these angles there. So this is very useful to cover large parts of the ground, cut down survey times by 4 or 5, but still know exactly how much we can trust this data. So that goes to the idea of surround sounds. How to actually use these different angles to the best effect. With multibeam sonars, we're imaging a particular target or a patch of seabed and looking at the backscatter coming back. But what happens if we look at all the other regions in which it's scattered? And this is something we did, for example, with buried toxic waste. And that's something where we compared scaled experiments that we did in our tank at the University of Bath. So in 2 meters of water, with calibrated seabeds, calibrated targets that were placed proud on the seabed or buried at different depths, imaging from different angles, and then comparing it with data at sea from the Stockholm archipelago with imaging with sonar and imaging on a chain at different depths, the scattering there. So we were able to find out what the best angles were for imaging. And we went on dump sites like this one to look at particular targets and find out how dangerous they were. So first, what they were made of. Is it rock? Is it a barrel? Is it a barrel still full of toxic gas? Or has it corroded a long time ago and all the gas has left? Is it worth cleaning it up right now or not? So the full-scale results in the field were fortunately very close to the experimental results in the lab. So I was very relieved. But all these differences there tell us what the target is made of. And we summed up these results in this book about the CETA project, the European project about imaging buried waste in the seabed with a lot of ground truthing, of course, and imaging all these different sites. So surround sounds are going to be very useful to understand what's going on, not only looking in the backscatter direction, but looking in other directions. There is a similar approach which is used in subsea geophysics by a company called Pangeo Subsea and Acoustic Zoom, which has an acoustic core. In that case, they place it on a tripod on the seabed. They have different types of transmitters, low frequencies and high frequencies, and they receive at lots of different angles and rotate it around the seabed. And that enables them to get acoustic cores over maybe a 15-meter radius down to 30 meters to delineate the different layers, but identify, for example, boulders that might affect drilling or gas pockets, anything that might be a danger there in the subsea bed. Jacques Guigné, a colleague who did his PhD at the University of Bath, has his own company. And we explained this approach into our book, Acoustic Investigation of Complex Seabeds, that explains all the science behind this acoustic zoom concept. But not only are we using the sounds that we create and using surround sounds to get information about the different types of targets, we're also surrounded by sounds. These images show spectrograms of different sounds around the ocean. The x-axis shows the time. It varies between a few minutes or a few milliseconds. It shows on the y-axis the frequency, varying a lot depending on where we are. And the colors represent how loud the sounds are. red, very loud, blue, not loud at all, or background noise. And we can find all sorts of information. For example, snapping shrimps create short, loud noises lasting a few milliseconds. Other type of fish, like haddock, have their own sounds there. This is from an article that we did with Nathan Merchant when he was at the University of Bath, looking at the sounds of shipping in the English Channel. We can look at ships over smaller times, and also find transient events associated to processes in the oceans or long-term trends as well. So there are lots of things that we can do there. When we look at all these different frequencies and how loud they are, we're guided by the Venn curves. The Venn curves there are representing as a function of frequency on the x-axis and sound levels on the y-axis, how loud different sounds in the oceans are. The results from compilations over the last 50, 70 years by underwater acousticians, and they give us a good idea, for example, of how noisy the sea is, just from the sea state. A flat sea is going to have a frequency curves that look like that. As the sea gets rougher, we have more waves, more bubbles, it's going to get louder and louder. We can find the frequencies associated to different types of ships or different densities of ship traffic. We can see the noise from the rain, from the wind, all sorts of things. So we have a good idea. But there are still lots of gaps in these places. For example, low frequencies below 1 kilohertz. We still don't have that much information about what's going on in different oceans. And Shola Garibo at the University of Bath is doing a lot of work identifying all these different low frequency ocean processes. If you're interested, she is doing a UKAN Plus webinar on the 29th of July in just 2 weeks. So I would strongly encourage you to either attend the seminar or watch the recording on YouTube later. When we look at sea states, we have surprises as well. For example, we have been in Svalbard with glaciers and icebergs. The sea was very flat, so we would expect a very low curve. And actually, the sound was like sea state 4 or 5, very loud, extending into the higher frequencies. And these sounds are associated to the ice itself, to the melting of icebergs or small blocks of ice. And as climate change is changing the environment, making the glaciers melt and melt faster, we can record these changes with underwater acoustics, and we'll see some examples later. Finally, another thing which is very interesting is in terms of animal vocalizations. People have focused on the loud animals and marine mammals as well, for example, to protect them and understand them. But lots of fish and other animals like crustaceans are making noises which can be very loud as well. That gives us a lot of information about the ecosystems. This image there shows a picture from a glacier in the Arctic. We're going to see part of it there collapsing into the ocean. So it's called calving. This image was taken from stereo cameras we had on the shore, looking down at this glacier in Svalbard. This is 60 meters above the water, and we still have a high amount, several tens of meters below the sea surface as well. So this is a big glacier there. Not as big as the ones in Greenland, but still significant enough. When this glacier melts, that's going to create mini tsunamis. They are not that important here because there are not many people, but in other places like Alaska or Greenland, melting glaciers have been known to sink some boats, destroy some pontoons or houses, and even kill a few people sometimes. So it's important to know when they occur and where they occur. And for that, we can use acoustics. I'm not sure the sound is going to translate at all in your recordings, but what we can see at the top there is the sound pressure. And we can see some bangs or cracks there, and we can hear the blocks of the glacier. So just the video we saw earlier, we can hear them coming down to the surface, rotating around and creating more noise. The spectrograms give us more information as well then. So what we can do is use these sounds to identify the noise sources. Where they are, we can do that by using at least 2 hydrophones to triangulate where it is happening. They make different noises depending on whether they are falling from the surface of a glacier or they're coming up from below the sea surface and bobbing up to the surface. And suddenly we have a huge block of ice that creates some waves and a mini tsunami as well. And that gives us information when it's happening, so we have time to prepare if we're on the shore. I have been in one of these mini tsunamis myself, and it's not a pleasant experience. Just in this place, so we were in Svalbard, we're in a small boat, just a Zodiac size. And because I was the youngest and tallest of the team of 3, my task was to jump into the water and help carry the boat on shore. And just as we're approaching the shore, we heard a loud bang. We looked around and said, oh yeah, nice one, nice block. I didn't think much more of it. So I jumped out of the boat, and suddenly I felt all the gravel underneath being sucked from under my feet. So I was in water up to my ankles, and suddenly I was in water up to my nose. So luckily I had the Arctic suit, so it was not too wet, but I was just clinging to the boat, and we saw a 15-ton iceberg crashing just a few meters from us. That could have been very dangerous because, well, it could have crushed us, or if we had been unlucky, it would have crushed all the equipment and left us without weapons at the mercy of polar bears and with no means to radio back to base saying, please send help. But mostly we felt very stupid because as scientists, we should have known that that was a big block of atmosphere, and the small waves we could see in the distance would translate into bigger waves around 1 meter high when they arrived on the shore. So that's why acoustics can help a lot. Other things that people have looked at are the impacts from offshore activities. Earlier, we talked about renewable energies. For example, tidal turbines, wave energy converters. How much noise do they make? What we've been able to do with several collaborations with the University of Exeter is, for example, measure the acoustic emissions from wave energy converters. And these show the power takeoff trains at every time, just taking the energy from the waves, creating electricity. But we can see how noisy it is. It's not very noisy, but in all sea conditions, we can still detect it 200 meters away. It's a very fine signature, but looking at the right frequencies, we can find it. And we use that for condition-based monitoring. The same way that when you're driving or cycling, you can hear a noise that doesn't sound right. You know you have to go to the repair shop at some point. There, we can use these noises to find out what in the device is making noise, whether it's the right kind of noise, or we need to schedule some repair or some monitoring there to see how well it works, and whether we have to find something when we have a good weather window and send a ship to repair it. We can also compare these noises to shipping and marine life. In that case, that was work we done with Nathan Merchant and Joe Garrett. And we've been able to compare over several years of measurements. There is a gap there when, so that's a few months, when recovering one of the instruments and a false manipulation erased all the data. But otherwise, we can see how loud this is, compare the amount of shipping, and realize distance shipping in the English Channel is much louder than the noise we make with marine renewables in Falmouth Bay. And the frequencies we make the noise at and the sound levels are not harmful to marine life. So green energy at sea really is great. Talking about mitigation and looking at how the noise affects animals, other offshore activities include seismic exploration. This image there shows a typical seismic vessel. Seismic exploration, by making loud bangs in the sea, is very noisy by nature. And I've been fortunate enough to do several knowledge transfer partnerships with SAGE Limited, looking at mitigating the impacts from seismic prospecting. So working with the industry to make sure that it was as good as possible with marine mammals and respecting environmental guidelines in the different countries. The traditional way to do that is to have marine mammal observers who would look around with binoculars, maybe detect a faint thing very far on the horizon and say, this is a whale, but then you need to decide whether it is within the mitigation range and whether it is really a whale and not just something in the sun. SAGE has created infrared cameras with stereo vision that can actually detect how far the animals are and say whether they're within the mitigation range or not. But that's if the visibility is good and if the animals are at the surface. So marine mammal observers increasingly use passive acoustic monitoring, listening to the sounds of different types of animals, detecting where they are, what they are, and whether they are close enough that seismic activities need to be stopped or moved away. But that relies on the animals vocalizing. What we can do is think about these seismic sources as sources of opportunity that would help us detect if the animals are not vocalizing, but they are still around. This cartoon from New Scientist is actually showing a seismic vessel with seismic source there. These sources are very loud because they need to penetrate hundreds of meters and kilometers of seabed to find oil and gas deposits or geohazards and come back up to the surface. And some of the sounds might come up through the water column there. They might be emitted in other directions, and they might have higher frequencies that we can all use to detect hidden animals using the air guns as sources of opportunities. And this is work that is led by Nikhil Banda at SAGE and that we are participating with. How loud the sources are, we know what it should be in open, deep water. As soon as we move to more complex topography, variable environments, for example, when we have fresh water coming in from rivers, or when we have variations in temperature, this is going to vary a lot. And some of the work done by SAGE has been putting the facts and measuring what the sound levels are. For this source, for example, we would expect a spherical or a circular sound footprint. What their measurements done with drifting buoys have done has shown how asymmetric this is. So the mitigation zone, which extends much further away, can be reduced in some conditions, but has to be expanded a bit in some conditions as well. So this is really giving the facts, giving the data for the exact shape of a mitigation range. From a scientific point of view, when do we have enough measurements? How well do you know these shapes? How does it change with the tides, with the temperature, with the sources, with the sea conditions? That's where we can use techniques like 4D VAR or artificial intelligence, and we have been able to do that with other companies in other settings as well. All this feeds into the bigger theme of long-term monitoring. Very often now, many countries or companies deploy instruments on the seabed for a very long time to listen to sounds for up to years at a time, or for seafloor observatories for many years, sometimes decades, like in Canada, where they can have 15 years of data about sounds in the ocean. That way we can find out if ships are increasingly noisy, or we have more shipping. We have less whales, more whales. Are the oceans warmer, less warm? All these different things, we can find it out with acoustics. This is something that has been done at the European level with the Marine Strategy Framework Directive, which is looking at good environmental status, so making sure we don't create too much noise in the ocean and making sure it doesn't affect marine life. The Marine Strategy Framework Directive is telling us about the frequencies associated to shipping bans, for example, to monitor how much shipping we have. And this is feeding into bigger efforts, making sure we compare like with like. I'm involved with British standards, which has been instrumental in telling the other countries what they should use for acoustics, feeding into the international standards in underwater acoustics, how to measure noise from different sources like ships, pile driving, how to compare different types of noises. And we also do that at a different level with the international quiet ocean experiments, where we want people to compare with the same standards and the same metrics and see how the oceans are evolving, what is our role in it, and how we can help protect them there. The problem is big data. This graph just shows that the computing power is more or less reaching a plateau now with Moore's law, so we are reaching the limit, or we're going to reach it very soon. And the scaling law about how many chips we can put on the computers has broken down already. As we have more and more data, every 2 years we create more data than we have created in all of history. How do we bridge this gap there? Do we need to keep all this data? Do we need to process all this data? And then we can look at the known unknowns. For example, we know we have whales and ships. Where are they? When are they? We can find out. What about the unknown unknowns? How do we detect processes that we didn't know were making noises, or sources of sound that we didn't know were around? So how do we detect the unexpected there? That's what we need to do in underwater acoustics research and in the applications. With the International Quiet Ocean Experiment, I'm co-chairing an international working group on Arctic acoustics. We started in late 2019, and we have been organizing different activities. A virtual workshop in 2020 that was with people from different continents working with the Arctic. We have participated in other conferences to do with Arctic sciences in general, showing the point of view of the underwater acousticians and how acoustics gave us information about these faraway places. We're able to feed into topics like the Arctic Science Ministerial. The last one was in Berlin in 2018, and we're very pleased to have politicians listen and say, wait, yes, we need more acoustics. We need observatories around the Arctic, because this place is very susceptible to climate change. At the international level, underwater sound is now an essential ocean variable. So all the new activities in the oceans for monitoring the oceans are encouraged to use underwater sound. And right now, in a few months, we're going to have in the UK, the UN Climate Change Conference, COP26, and sound is going to play a big role in there as well, from what we saw from the preparatory events. So just to wrap up this kind of tour of how we're surrounded by sounds, how we can use the surround sound to better understand the environments around us, better protect this environment. We have to think that not only we're surrounded by sounds, but we are part of the time continuum. We are surrounded by time. I like this image very much. It was from an article in Science, and it shows, as time goes on, from 20,000 years ago, 10,000 years ago, the end of the Ice Age, the differences between what happens on land as it's getting denser, more populated, more polluted as well, what happens in the oceans? The present is there. What are we going to make of the future? And what we can do is work together as underwater acousticians, but with other disciplines as well, to make sure these oceans can stay as protected, as sustainable as ever, all thanks to underwater acoustics. I will stop the talk there, and I'm very happy to answer all your questions. Thank you. Okay, I don't see any questions coming in now, so feel free to use the Q&A, or if it's too difficult, use the chat. I can monitor both channels now. It always takes a bit of time to type the questions. Oh, thanks, Nick. I have a question from Nick Shotiros. How far can you detect marine mammals underwater using sound? That depends on the frequencies they use and how loud they are. The loudest animals are the blue whales. They transmit at low frequencies, so we can detect them. So these low frequencies propagate over very large distances. They don't attenuate as much. And the blue whales are very loud, so we can detect them at hundreds of kilometers. Other animals are going to emit at higher frequencies. They're not going to be as loud, for example, some fish. So we're going to detect them a few tens of meters away. But they're still useful to know, for example, how they live in a particular habitat, how many fish there are. Some animals, like snapping shrimps, are very loud, and they can swamp underwater acoustic communications in some conditions, for example, in the tropics. So how far we can detect marine mammals, I would say up to several hundreds of kilometers, if not 1,000 kilometers, for the loudest ones. For others, that could be hundreds of meters, which is good enough. For typical protected mammals in seismic exploration settings, that would be beyond the mitigation range, so that would be up to 10 kilometers maybe. Okay, other questions? What can we do to mitigate man-made noises? Thanks a lot. What we can do is make sure our noises are not as loud. Okay, sounds obvious, but that's still something we can work out. For example, with ships can be very noisy based on how fast they go. On the Canadian West Coast around Vancouver, there is a program called ECHO, where ships that go in and out of Vancouver Harbour have to go above a rail of hydrophones. And they get a certificate telling them how noisy they are or how quiet they are. But that tells them how loud they are at different frequencies and at different speeds. And then they are told, okay, there is a pod of whales at this distance, so please slow down to make less noise. And then you can accelerate and go faster once you're away from them. Or based on the noise they make, they can go faster because that's going to be less harmful, but stay a long time around the whales. So that's a way of measuring these different sounds. What we can do as well is make sure that we don't emit loud sounds in places where animals are, where they're protected, where they're very susceptible to these noises, which is what the seismic industry is doing, because they don't want any dead whales washing ashore. They want to protect marine life. So they want to know whether animals are within the mitigation range, and they have to stop the noises. After that, what we can do is think about the tools, so create new tools or use tools in a different way to create less noise. For example, with multibeam sonars, we use higher frequencies. They're going to be more attenuated in water. We know how much impact they have. And sometimes we can actually see the animals. For example, with the renewable energy example I showed, we can see the animals moving around and sometimes getting very close to our sonar. So we know they are not bothered by that. So creating less noise or being more mindful about the noises we want to create or that we need to create. Question on the Q&A. Can you expand on how we can use active acoustics to detect hydrothermal vents in the deep ocean? Is there a depth limitation for using different sonar techniques? I will answer the second part about the depth limitation. First, there is no limit to sonar. We can go anywhere. That's the beauty of underwater sounds. We can image down to the bottom of the deepest part of the ocean. We can image sideways for hundreds of kilometers. So we can have no limitation there. Hydrothermal vents, when you look at them on sonar images, they would be small bumps, small cones, and we don't know if they're active or inactive. If the image is high enough in resolution, we can find out they are not like volcanic cones, they're very different. If we know a bit more about the geology, we can say, yes, for sure, these are hydrothermal vents. Some of them can be quite big, like the Tag Mound in the Atlantic, which is around 100 meters high and several hundred meters deep, several hundred meters wide, made of hydrothermal deposits. But the vents themselves are going to be smaller. What I found from experience is that as we go closer to them, the hot water is going to affect the penetration of acoustic waves. So, for example, when we move with a multibeam sonar mapping the seabed, the multibeam sonar has a particular width. It's covering, let's say, from 60 to minus 60 degrees on each side of a ship. As you go above the hot water of events, suddenly it reduces to maybe +5, -5 degrees. So this is just an indication that something strange is happening, and we can go back to high-resolution acoustics to map it and prepare the future dies that are going to give us the images there. I hope this answers your question. If it doesn't, feel free to come back, of course. A question from Diego Miguez. How transferable is the acoustic identification of marine life? Do they have to match precise frequency resolution and temporal windows for a precise species to be correctly identified? That's a very good question, because this is a very wide research field. The easiest way to identify fish, for example, is from their fish bladder, which is gas, is going to have a higher acoustic contrast. I remember when I started in that field, some people were modeling salmon seen with acoustics, and the fish bladder of a salmon had exactly the same backscattering strength as a golf ball. So they were playing with golf balls in a pond to try to find out how good the new sonars were going to be. But the gas bladder of a fish is going to contract as they dive, but not always. Some of these fish don't always contract it in the same way. Some fish don't have a swim bladder. Some fish are going to be too small, or some marine mammals that don't have a swim bladder. So we have to find other ways, and very often that's going to be based on studies of individual fish to find out what they are at different frequencies. Fisheries sonars use different frequencies to recognize fish of interest to fisheries, so cod, herring, and they are good enough to identify, for example, cod at different ages. So differences between juvenile cod that you should leave alone and mature cod, which is good for fishing, or make the difference with a herring that you don't want to fish right now. So that's for the frequency resolution, the identification of marine life. The temporal windows, that's going to be related to the frequencies, that's going to be related to how people use that. Very often we use ping rates of a few times per second. So that's good enough to identify the animals. And I hope this answers your question. Again, feel free to come back. Nikhil Banda asks about detailed views on machine learning and future on underwater acoustics, for example, target detection. Well, thanks, Nikhil. I'm not sure I'm the best one to ask, but machine learning is all over now. That's the new fashionable trend, the new buzzword. We all have to have machine learning in our proposals, in our projects to look really nice and trendy. Machine learning is very useful, but we have to think about how we use it. And sometimes we have been using it for years without calling it machine learning. It's like geographic information systems. When I started in the field, geographic information systems, GIS, were all the rage. Everybody had to do that. We had lots of buzzwords, lots of jargon, but when you dig down a bit more into it, you realize people have been doing geographic information systems for years and decades before that. They just didn't have this fancy buzzword. So geographic information systems have new tools, new functions to find more data. Machine learning, that's the same thing. So some of the techniques we have been using, like supervised clustering, unsupervised clustering, have been used for ages, decades before that. But there are new tools that we can tailor to underwater acoustics, but we still need to be very careful about how we use it. So either making sure there is a human in the loop, or making sure we ground truth and validate how it works and make sure it's traceable. One example that people move around is, for example, the identification of animals on images for photo banks. And one machine learning algorithm was very good at distinguishing horses from dogs. It had close to 100% classification rate. But someone decided to say, well, both animals have 4 legs. How do they do that? How they can always find the horses so well? And they found out that the algorithms were not focusing on the animals themselves. They were focusing on the small trademark at the bottom of the image that says this is from the horse data bank, from this horse data bank. So it was actually focusing on some copywriting at the bottom of the image there. So traceability is going to be very important, especially as we trust machine learning and artificial intelligence to take decisions for us. For example, we could imagine having an observatory on the seabed, monitoring the noise from a ship, and then having an algorithm telling the ship, okay, you're too noisy, get out of there, we don't want you in a harbor anymore, or go to a different shipping lane, or it's okay, you can proceed. How can we trust that the algorithm is taking the right decision? For example, work we've done in the Arctic, and we're still doing now, shows that the shipping bands are strongly affected by the presence of ice. So when there is no shipping at all, we still have noises that tell us ships are around, even if everything is covered by ice. So some of these metrics have to be tailored to the environment they're in. Okay, other questions? If you're interested in machine learning, there is a nice article in the Journal of the Acoustical Society of America by Peter Gerstoft from Scripps and his team, talking about the different types of machine learning, what is useful for underwater acoustics, what has not been studied yet. And there are different tutorials about how to make it work as well. So it's coming to the fore, it's increasingly useful, but we still have to be very mindful of what we use it for, what it tells us, and how much we can trust what it tells us as well. Okay, I'm still waiting for the next questions. But this problem of traceability, repeatability, and trustworthiness are important in any field of acoustics. I remember when I started with sonar, with side scan sonar, I wanted to understand how to interpret the sonar images. And I was asking my geologist colleagues for an interpretation of an image, trying out my image processing algorithms to get as close as possible to their own interpretations. And it was very disheartening because sometimes I was coming back 2 weeks or 2 months later. Their interpretation had changed because they had other ideas, because they had read other articles. So their interpretation was not stable in time. And that's why we have to be careful about how we interpret images. If we're used to working in continental zones, for example, we might interpret sonar imagery in a very different way when we move to polar water or to deep abyssal plains. That was one of the motivations behind my books on side-scan sonar imagery and the handbook of side-scan sonar, trying to make it more systematic and using the best techniques from all these geologists who know how to interpret the images, and making kind of a checklist about what we should look at in these images. And that's true for everything. That can be true for spectrograms, looking at passive acoustics. That can be looking at the topography with multibeam sonars, or looking at seismic profiles as well. So all there, we have to modulate the experience with the repeatability and what the machines can tell us to make it more systematic and something that we can fully trust each time. Okay, I see we're moving close to the end time. So thank you all for attending. This seminar has been recorded and will be available on YouTube soon. And you can check it on the UKAN Plus website as well. I'm just scanning in case any last minute questions are coming in. But thank you all for coming, asking your questions. Thank you to UKAN Plus for making this series of webinars accessible. I have used some of the previous recordings a lot. I would like to flag out the seminar from Jo Garrett a few months ago now, where she presents the Sonic Kayak, which is a very nice and cool tool to use to do acoustics in everywhere around us. And remember, there is the webinar by Shola Garibo in 2 weeks, advertised on the UKAN Plus website as well. So thanks a lot. If you have any questions, feel free to ask me via UKAN Plus or find me on the web. And it has been a pleasure talking to you. Thank you.